Multiple references to the Boolean object, are they immutable? I'm not even sure what that means. So what do you mean by immutable Boolean objects?
So I had I had made a new Boolean, and then I would make a second Boolean that would point to the first one, and it would get the right value if, you know, you had just done it. But if you changed the first one's value or the second one's value, they weren't linked up anymore. So
Correct.
I ended up using a atomic Boolean because then I can have two references to the same object that could be changed.
Well, so this is where methods can help you, right? So if you have a Boolean that is somehow significant, right? You have two ways to get to its value typically. One, you can either refer to it directly. So if it's sitting inside, game board bracket I bracket J dot box dot left, right? You can refer to it like that instead of making a copy of it. Or you could put a method, in your box or your game board, and access it through an accessor like that. But I'm not sure you definitely don't need to. I'm not sure I would recommend getting into atomic booleans to make that happen. I mean, why not just reference the object with its wherever it's living, instead of trying to have two instances of the same object.
It was just because I was trying to make the right side of one box be the same object as the left side of a different box.
Okay.
That was why I was doing it that way.
Okay. Um, yeah. Hmm. So yeah, if you use booleans with an uppercase B, you should be able to do that. Um, you should be able to make them both the same object. Booleans might clone when you do an equals assignment statement, though. So yeah, that is tricky. So maybe that's a good case for atomics. Um,
Okay, I just wasn't sure. I knew that it seemed like it was more used for multi-threading is what I
right,
was reading
right.
on. But
Yeah, I'm a little surprised that that would actually take care of it. And it may be a side effect that in order to make it atomic, it needs to keep it updated or something like that. If it's working, then that's fine. If it feels a little mysterious, keeping your fingers crossed, holding your breath kind of thing, then maybe you want to find a different way to do it. Um, and maybe instead of a boolean, maybe define your own class that will let you sort of control. Define your own class so that if you have two things that reference the same instance of that class, they're actually the same thing. Um, but I haven't messed with that. That would be interesting to play around with, though. But like with rectangles. All right, so there's a rectangle R1. And there's a rectangle R2. So if you say R2 equals R1, I'm pretty sure we'd have to double check this. Let's just try this, because this will get us into a deeper discussion of cloning objects. So let's try something. So here's the experiment, right? We'll make R2 equal to R1. We'll print out R2. It should be a 5 by 7. Um, and then let's change R1 to be a 1 by 2, and let's print out R2 and see if R2 changed. Length and width. Length and height. All right. Right. Did I mess up? I did mess up. All right. So same thing. So yeah, R1 is a rectangle. R2 is set equal to R1. And when you change R1, R2 changes, right? So R2 is, in the language of pointers, it's a pointer to R1, but it's a reference to it. And so this should work with Booleans, right? What you're doing. If the edges of our boxes were rectangles, right, and the right edge of this box and the left edge of this box both referred to the same object, then if you changed it on account of clicking in this box, it would change when you looked at it on account of that box. So yeah, R1 and R2 are basically referencing the same thing in memory once we do this. Booleans may not do that though. So there's times when we do this and we're basically copying a reference to an object. There's times when we do this we're actually copying the value of an object. For example, if R1's an integer, then this simply sets R2 equal to the value of R1, but then if we change R1 later, R2 is unaffected. Right? So it's a question of cloning, right, or copying versus making another reference to. Right, which is why we don't have to construct a new rectangle with R2. So I think it depends on the class, and I honestly don't know about Booleans, but let's find out. So let's set flag 1 to be a Boolean, which is false, flag 2 to be a Boolean, and we'll make it the same as flag 1. And then we'll set flag 1 to be true, and we'll see if flag 2 changes value. Alright, so this does not happen with Booleans, which is what you've discovered. With Booleans, when I copy flag 1 to flag 2, it seems to copy the value of it, but flag 2 is its own object, which is very strange. So I think you can get around this by making your own version of a Boolean, right? Make a super duper Boolean that basically acts like a Boolean, but that will circumvent whatever is happening here that's causing this to copy the value instead of the actual reference. Yeah, I find that very strange, but it appears to have created a new instance without a new keyword. Yeah, so that's interesting. Yeah, it is very peculiar, and I'm pretty sure that if you were to Google, um, do Booleans copy values or reference, you'll probably find some heated discussions on Stack Overflow about that and why that's a good or a bad thing. But this ties into to something else that may come up in possibly PA4, possibly PA5, but certainly in other courses beyond this. Definitely found posts of people talking down to those. Yeah, but you can find people talking down anybody for asking any question, right? Where it's like, please learn to properly phrase a question if you expect an answer, kind of thing. Or this doesn't belong in this forum. But this is a general question, which is how do you make a copy of an object, right? So suppose I have a linked list, list 1, and I say list 2 equals list 1. Well, that's pretty clearly just going to make a reference to the same linked list, right? And if I add something to list 1 and I look at list 2, it's going to have that thing in there. But what if you actually wanted to do a copy of list 1? If you wanted a new linked list that was completely independent, had its own existence, and it's a hard question in general. So objects come with a clone method, right, which will attempt to make a copy. So creates and returns a copy of this object. But the precise meaning of copy may depend on the class of the object. Right, so it'll give you something that's not going to be the same if you do an equal equal. But there's this notion of deep copy versus shallow copy. And if you think about a linked list, it's a bunch of boxes with arrows. And if we wanted to make a copy of this list, what we'd like to end up with is a new set of boxes, a new set of arrows, with the same values inside each box. But suppose it's not a linked list of integers. Suppose it's a linked list of strings, or a linked list of rectangles, or a linked list of hash maps, right? You can create new nodes and new arrows, but what about the hash map that's inside? Are you going to copy the reference to this object, or are you going to copy the contents of the object? In other words, are you going to have both of these things pointing to the same string, or are they going to each point to a different string? And so a simple notion like making a copy of an object is potentially a lot more complex. So a shallow copy is really just kind of a first level copy. We would have, for example, a new set of boxes and arrows, but they would point to the same object. And so if I add a new box here, I don't see it down here. But if I change the contents of this box, I would also be changing the contents of that box. Okay, that's a shallow copy. A deep copy, everything would be completely replicated down here. If this was a string, I'd have a new copy of the string down here. If this was a hash map, I'd have a completely new hash map whose contents were completely independent of this hash map. And if the values stored in that hash map are strings or linked lists or hash maps or linked lists of hash maps comprised of strings, right? You have to sort of go down this big tree of objects and make copies of them. So I think copy and clone are more or less the same thing. But there's shallow versus deep is really the difference. Um, but assignment is A equals B generally is just making this a reference to whatever that's a reference to if these are objects, although apparently not for booleans. And the equal statement will sometimes call the clone method of this and take the result and put it into A. But like I say, there's a notion of a shallow copy versus a deep copy. And it's a question of how separate is this copy from the original. I missed a bunch of things in chat here. Bracket conventions bring out much anger. That sounds like a fortune cookie. Paired with a fedora hat and 20K post calls you an idiot. Yeah. So clone is the name of a method. So let's look at linked lists. So there's a clone method inside linked list which says returns a shallow copy of this linked list. So the elements themselves are not cloned, but the nodes are cloned, right? So if I make a shallow copy of a list and I delete a node from the original, it doesn't get deleted from the copy, right? But if I change the contents of node 5 in the original, it will also change the contents of node 5 in the copy. Or rather, if the thing in node 5 gets changed, right, then the thing in the copies, node 5 would also get changed. But objects have a clone method, so there's always a default clone method. And the default clone, I think, just makes another instance of the object. Oh, I would name a depressed parrot copy. Interesting. All right, in PA4, do we need to worry about, yeah, you asked this before and I forgot to answer it. In PA4, do we need to worry about the little yellow triangles that pop up in Eclipse? You can hover over them and see what they're saying, but they're usually kind of more stylistic things, I think. If it's, something like, warning, this could cause the sun to collapse. If it rains when you run this code, then you might want to change it. But if it's usually, this is a serializable object that doesn't have a unique ID, or the default package is discouraged, or this should be uppercased, or something like that. You can hover over them and see what it says, but usually not an issue. The yellow triangles thing says clonable. Yeah, so they're probably safe to ignore. I don't know what it means if the yellow triangles say clonable. Pop by office and maybe you can show me. All right. Yeah, that would be a good warning to pay attention to also. Yeah, and I think every time that you make something in Eclipse, you get that warning up front about a serializable object. And oh no, not a object still skin. And you can resolve these, right? So you can say add a default serial ID version, and you get a cool little extra line in here. Um, but it's stuff that's keeping the compiler or the system or the universe happy, but doesn't necessarily affect your code in in any significant way. Some of these are like unused. This import's never used, and it's warning you about it. So you can remove it. You can click on this, and it'll remove imports you're not using anymore, and things like that. But I'm not going to worry about them, right? I'm not going to take off points for having yellow triangles. All right, so you ready to talk about networking? Let me close this out. Yellow triangle Tuesday. All right, let's go for it. So networking, right? We're in this connected paradigm where computers can talk to one another. We can swap files from one machine to another. We can browse the web, which is really just looking at files stored on other machines, um, and so on and so forth. Um, so how does this work? There's a number of different levels to what's going on when you make a connection to PuTTY or to the Linux server through PuTTY, or you go to a web page, or you send a piece of email, or whatever you're doing. Um, so let me start off by talking about this idea of client server. And this is really the model that's in play in most of these things that we do, whether we use PuTTY to log in to the Linux machine, which we call the Linux server, that's a hint, or we go to a website and ask for a page, or we try to send something to our printer, or whatever. Client server model is sort of a general setup for this, and the basic picture looks something like this. You have something called a server. It's a piece of code running, but we think of it as a resource that's usually shared that basically accepts requests from different entities and then does some action based on those requests. And so the entities that make requests, those are called clients. And actions are initiated by the clients. Yeah, this will relate to SSH. Um, Actions are initiated by the clients. The server kind of hangs out waiting for, I'm so bored, what should I do? And then a client comes along and says, hey, poke, 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 can you do something for me? Right? And the server says, yes, and starts dealing with that client. So typical examples of this, right? A print server. So I have one printer sitting here under my desk. I can print to it from several different devices, including my phone, different laptops, and so on and so forth. Um, if I had, a connection, a wire going from each of those devices to my printer, there's the possibility that two devices would start printing at the same time. And that would be unfortunate because their bits would get confused with each other, right? This happens sometimes with old setups. Um, and so instead of having these clients talk directly to the physical printer, they talk to a piece of software called a print server. And the print server is the only thing that directly connects to the physical printer. It's actually a wireless, but that has the ability to actually send things to the printer and cause it to print. And so when, client 2 wants to print something, it sends a message to the server, piece of software running, and says, hey, I got something I want you to print, here it is, right? And the server is the thing talking to the printer. So if it knows that client 1 sent it something and that thing is still printing, it will hold on to what client 2 sent until client 1's job is done printing. And then if there's nobody else that's already asked for a print request, then it'll go ahead and take what client 2 sent to it and send that to the printer. So it's like a centralized access to this shared resource. All right, so that's one application of a client-server model, is you have a single resource, but you want to share it among different entities. Print server, typical example. Another example would be, a machine that we want multiple clients to be able to access. So, for example, Linux, engrcs.com. So our Linux server. And the clients are, you and I who want to log in and do things on that machine. And in this case, there's a single program running, and it's called SSHD. So SH is the Bourne shell, right? That's the shell before bash, which is the born again shell. So this is just the plain old Bourne shell sh. SSH is the secure shell, and SSHD is what we call a daemon. A daemon is like a demon, but spelled differently, and it's basically a server program. So SSHD is a program. It's hanging out on this machine. And it's basically waiting for clients to come along and say, poke, 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 excuse me, can you start a login session for me? And so if we hop onto the server, I need this to be wider. Right, so there's a process here. It's process 796. It was started on March 5th, last time I rebooted the machine, called SSHD. Yep, we got daemons and zombies. That's why Unix is cool. And process 796, that's the parent process of process 39710, which is, guess what? That's something owned by Nick. Which is the parent of something else, 39720, which is also owned by Nick, which is a bash session. So bash is, running right now. It's this program that's showing me my prompt and waiting for input and so on. That was created ultimately by this process, 796, which is the SSH daemon. Oh. Yeah, that's pretty mean to be scamming people like that. Every now and then someone would send out a spam saying like, I thought you should, chain mail, right? Like, someone just sent me this and it saved me in the nick of time, apparently I had a virus and it's really contagious, and you can check to see if you have this file on your system, and if you do, then you're infected. And it wasn't like system32.exe, but it was something like that. It was a critical Microsoft file that nobody had ever heard of, and you find it and it's like, oh no, and so you delete it and then your system crashes, right? Um, yeah. All right, so this is why it's called a Linux server, right? It's a server in this client server setup. So what is your client here? Well, it could be PuTTY, and if you're on a Windows machine, you say PuTTY Linux engrcs.com. PuTTY is a program that you're running. It's a client program, right? It could also be SSH. That's also a client program. It's a C program that gets keystrokes and sends them through this networked connection to a server, right? A program sitting on a remote machine, and then takes things coming from the server and displays it to you. And there's a zillion clients. So one of the oldest clients is called Telnet, and we'll play around with Telnet because it's a really lightweight way to send and receive information. It's not secure. It's not like SSH where there's encryption in place, but if we don't care about encryption, Telnet's a good program to use to talk to machines. Hey, I think I have that uncle too. Actually, I go through my spam folder once in a while at Clark just for fun. And I had one yesterday. It's like I have $5 million. No, it's $5 billion to give to charity, and I've decided to give it to you. Please contact me for information so I can send it to you. It's like $5 billion, and somehow Clark marked that as spam. I don't know why. It was from a Yahoo address, so it's got to be legitimate, right? All right, so where else do we see a client-server model? So play Minecraft, right? So a Minecraft server, right? That is a server. And when you run Minecraft and you're running around and Steve is chipping up stones and stuff like that, that's the client program, right? Now you're using your mouse and your keyboard to move around and do actions, and those are simply inputs that are being sent across some kind of network connection to the Minecraft server, which is doing what it wants to do, right? Simplified version of it, basically the same idea. So this pops up in all kinds of places. When you want to send an email to somebody, right? There's a so if we're doing like older email systems, there's a mail server running on your machine. And when somebody wants to send mail to you, they don't just go directly into your mailbox and drop a message in there. They talk to the mail server on your machine. And that says, oh, this is mail for Nick. Do I know anybody named Nick? Yeah, I do. This is where their mailbox is. Okay, I'll go ahead and add this message to the end of their mailbox. So that's a mail server. A web server is another program. It's usually called Apache, that is running on a machine, and when you want to get a web page from a machine, you basically talk to that program and say, hey, I'm looking for this web page, and it will go through its directory of web pages and pull out that page and send it to you. Right? So this basic model is used everywhere, right? In our network. So in Java, right, we can create servers, we can create clients. It's really painless to do. We can, yeah, you gotta watch those clicks. If you try to do this in C, it's the same process as doing it in Java, but a lot more involved. We have to sort of get down to the nitty-gritties and deal with all of these low-level details ourselves. In Java, because we have objects, we can create what's called a socket object or a server socket object that will encapsulate all the weird stuff we have to do line by line in C. So we're gonna play with this in Java. It's going to be relatively painful, but there's going to be a lot going on underneath. Yeah, we're not going to do the painful version. You'll get to do that later on though in other classes. But it's good, you know. It's very satisfying when you get it to work. Um, all right, so before we talk about sockets, let's talk about files because they're going to work the same in Java basically. Um, so when I was in high school, we had a terminal in the library that was connected to a computer. It wasn't quite a mainframe, but effectively. And that computer was shared by, you know, a chunk of New York State. So about, you know, 15 or 20 different schools um, had access to that computer. And we could log on and you know, write code and stuff like that. Um, and you know, pretty quickly we became aware that there were other people using this computer at other schools, right? So this was, you know, in the 70s. It was long before networks were a thing. um, and so we knew there were people, you know, at Cornell or Horsehead or, you know, these other towns outside of where I was living that were using this computer, and we thought, you know, it'd be cool to be able to talk to these people. Well, there's no networking, but it turns out you don't need that. So here's a way that you can do networking without having networking mechanics. You can use files, right? So this will save your skin more times than you think in the course of your programming life. So let's say, you know, here's person one and here's person two, and they want to chat with one another, right? Well, you know, you could do this very, very sort of crudely by just saying, okay, I'm going to create a file called, you know, Nick, and I'm going to make, you know, this file called nick.txt, and I'm going to put it somewhere where person two has access to it. So let me call this Nick, and let me call this Tom. All right, so I'm going to make a file called nick.txt. I'm going to put it somewhere where Tom has access to it. And Tom can just look every now and then in this shared directory area, and if they see a file called nick.txt, they open it up, they can read a message from me. And after they've read it, they can delete it, and now I know that they've read this message. And they can reply by creating a file called tom.txt. And I'll just look every time that I log onto the computer and see if there's a file there. And if it is, I'll open it up and read it. I can see their message, and then I can delete it. And now they know that I've read that message. And so you know, we could do that manually, but you could pretty easily write a program to do that. That basically just continually looks to see if there's a file called Tom. And if there is, opens it up and shows me the contents of it and then deletes it. And Tom can be running a program that continually looks for this file, and anytime it finds it, prints out the contents of it and deletes it. And now, if you have, you know, a program doing this constantly, we can talk more or less in real time. I can type something, and every time I type something on my terminal and hit enter, it adds it to the bottom of a file called Nick. And it creates it if that file doesn't exist, and so on and so forth. Don't delete Tom. And so you know, you've got to get into a little bit of handshaking so that you know, while I'm writing this file, Tom doesn't read it and delete it before I finish writing what I'm doing. But that's the basic idea, right? So you can share information between two resources by using some kind of shared entity that I can write into and the other person can read from, right? And this is really no different from what we call a socket, except it's not as crude as having files sitting on the disk drive. right? It's a mechanism that's more a part of the operating system itself, but the idea is exactly the same. So what we're going to do is we're going to create a socket, and we're going to set it up so that I can write into this socket and Tom can read from it. And anything I write in here comes out there. And we could create a second socket that Tom writes into and I read from. Was there really a MySpace, Tom? Yeah, Hotmail's a legit ID. Oh, okay. Cool. So yeah, so this is exactly like a pipe. It just happens to be a pipe that goes from one machine to another potentially. But it's exactly the same idea as a pipe from 224. It's unidirectional. You can write into this end of it, and coming out the other end is this other stuff. And I can push, you know, a bunch of things into here, and when Tom gets around to reading it, they'll come out in the same order, right? So it's a FIFO in sort of the classic physical pipe sense. Go in one end, come out the other, and things can queue up inside there. And the only difference between a pipe and a socket really is that this socket can connect two endpoints on different machines. Whereas a pipe, we basically have, you know, two endpoints of processes running on our same machine. It basically abstracts away the underlying network, but you need to specify an address when you create your socket so that it knows, you know, which 2 points should be connected together. So in the creation of this, we're going to specify something like an IP address, 192.168.0.5 or whatever, to say, hey, you know, I want this end of the socket to connect to that person. And so this is where the client-server model is going to tie into this, because what we're going to have is we're going to have our server basically create a special kind of socket with a particular address on it that clients can say, hey, I want to connect to that socket. And every potential client knows the address of that socket. So not a swerver socket, a server socket. So a server socket is a socket with an address. And the address has two pieces to it. It has an IP address, like, you know, 10.0.0.4 or 192.168.0.81 or whatever, plus something called a port number, which is something between 0 and 65,535. I don't think 0 is legal. And this combination of IP address and port number identifies a particular server socket which is being monitored by a server. You can use something other than TCP/IP, but what I'm talking about is going to be TCP/IP. But there's datagram sockets and things like that. Pretty much everything uses TCP/IP. There's also, you know, 6-part addressing, and there's 4-part addressing. I'm just going to work with 4-part addressing. But, you know, we ran out of IP addresses a number of years ago, and so there's 6-part addresses now. So if you go onto a Unix machine and you look at the file /etc/services, this is a list showing you the designated port numbers for different services, different servers that could be running on your system. So port 7 is an echo. And theoretically, if you try to connect to a socket on a certain machine with a certain address and with port number 7, you'll connect to an echo server, which should just send back whatever you send to it. Now, most of these things are disabled on most machines. Sort of general security policy, you don't want a lot of open ports on your system because whatever's listening to a port is potentially a security concern. If there's an exploit like a buffer overrun or code injection or something, right? So most machines shut down most of these, but some of them still exist. So you know, you used to be able to hit a time server on port 13, a status server on port 11. So the FTP server was on port 21. We don't use FTP anymore because it's not secure. But 21 would get you a simple file transfer protocol. 22 is the secure shell. That's what we use when we try to do a PuTTY session or an SSH session to a remote machine. We're basically making a connection to the socket with port address 22. And the server code that's running, that SSH daemon, is listening on port 22, and when a request comes in, it starts a handshake to say, who are you? Let me see your credentials. It checks the credentials and says, okay, you're allowed to log in to this account, and it'll go ahead and log you in, and then create a new process to start your interactive session. What exactly are ports? Ports are basically part of an address. So it's these are just numbers that are agreed upon to say, you know, there's going to be one process listening at, you know, your given IP address at port 22, and that's going to be your SSH daemon. And then if you want to talk to an SSH daemon, you know you should ask for port 22. So it's basically an extension of the IP. Let's see. All right, so 22 is a secure shell daemon. 23 is telnet. So that's the insecure way to log into a machine. 25 is a simple mail transfer protocol, SMTP. 37 is a time server. 79 was the finger daemon, so you could use that to get a list of all the people who were logged into a machine. 80 is the World Wide Web, HTTP. That's the insecure version. 8080 is usually the secure one. And so each service that might be running on a machine has a port usually designated for it, but not necessarily. And these are just convention, right? If I'm making my own Linux system, I could make my own process, put it on port 22 or port 80, right? And somebody going to a web page on my site would be talking to my code instead of the web server. It's you know, works by convention, but these are just, you know, agreed upon. All right, wow, we're out of time already. So what we want to do tomorrow is we want to start looking at Java, and we're going to use Java to create a server socket, and we're going to see the mechanics for that, and we'll use Telnet to make a connection to it and start playing around with moving information from one machine to another, like this. Yeah, that did go super fast. Sockets and networks are like that. It's just fun stuff to talk about. All right, so we'll continue with this tomorrow. I'll see you next time.